All right, well, here we go. Linear algebra, here we come. So, vectors is what it's all about, friends. Okay, and so we talked about vectors. I'm sure you've seen them before in vector calculus, vectors in maybe in statistics, whatever. And it can be thought of in physics, of course, just an arrow like so. The length, of course, being the magnitude, and of course the direction, being the direction. Yes, we can always break them apart into pieces. So we got, your right-facing component, if you will, and your up-facing component here. And we can do all these games we've always done. If this is R, then, of course, that's R. This bottom side would be the magnitude of R. We'd say it like this, times the cosine of theta. And, of course, this would be the magnitude of R sine of theta. And that's no shock to any of us, of course. That's kind of neat. In this book, we're going to write them a little bit more, a little differently. So we'll write them. Come on, Jay. We'll write them like this, something like this, maybe 1, 2, or maybe you do a 3-dimensional one. Good for you. Or wait. Seven dimensions, Jay. What's that about? Yes, good for you. Do not get hung up that you have to be able to graph everything, friends. Because in the statistics world, we keep track of information. The guy's height, weight, I don't know, phone number, I don't know, library card number, sure, Netflix number, I don't know, password for is match.com, and so on and so forth and so on. Okay, it's just a list of stuff. Okay, in the statistics realm, this is where statistics really brought home to me the concepts from linear algebra and the concepts from vector calculus. The idea that we can look at vectors as something other than a line with an arrow, to me, just kind of blew my mind away. Like, oh, that's kind of neat. I like that. We will see vectors written like this as well. Okay, this is your book uses a lot of column vectors. I'm going to show you the difference momentarily. Okay, this guy here, if this was A, in the books they'll of course write A with a big with bold font. I'll use a little arrow on top of it when I denote a vector when I write it out by hand. Okay, this guy here, of course, would be A transpose, and that would be a column vector. So this is a row vector, and this is a column vector. Oftentimes, the books will use column vectors, and they'll just define, hey, my vector is, they won't say my vector is, they'll not say my vector transpose is, they'll say my vector is this guy. Okay, and they'll write it in that fashion. They may flip it and use B transpose because they may like that better, but this guy here takes up a lot less room than this guy does. Okay, so for printing purposes, you can get a lot more on a page. It seems, anyways, at least across the page, if you use column vectors. Not a big deal. Again, when you open up Excel, all you're looking at is a big matrix, in essence, and any one of the columns, I mean, this could be, there you have a list of numbers, that could be a vector just as easily as this could be a vector. Okay, well, that's not a vector, dummy. That's a vector. Okay, so whatever makes it better and easier for you to do is great. I don't know, suppose you had some vector U, and some vector V, of course. To add them, I think it goes without saying, although I'm going to go ahead and say it because that's what I do, that when you add vectors, they have to, or subtract them, they have to be the same, dimensionally speaking. And 2 plus 1 is 3, 4 plus negative 3 is 1, and 9 and negative 7 is dos. Pretty easy. What would happen if you took 2u plus 3v? Well, of course, these guys here are scalars. What does it do? It takes your vector, which, for instance, let's start off with a nice easy one here. Let's say my vector was this guy. This is the vector, clearly it's the vector 3, 1. Right, over 3 up 1. What if I took And let's call this guy a vector f, I guess, because I haven't used one of those yet. What if I did 3f? Oh, cool. Oh. Hey, where am I now? Well, I feel like I went over 9 now, because that's 3 times as far in the x direction. And I went up 3 because it's 3 times as far up in the y direction. Of course, the length here, square root of 10. This guy here better be the square root of 90, yes? 81 plus 3 plus 9 is 90, yep. Which, of course, is square root of 9 times bigger, or 3 times longer. So we just scaled the vector. We'll talk more about scaling in a little bit, but here's the deal. So 2u would be 4, 8, 18. And I'll do it in a couple of steps here so it's easier to see. Not for your benefit, for my benefit. I have a hard time doing math in my head some days. Getting older. 7. Negative 1. Negative 3. Bam, there's your answer. Nice. Okay. Boom, 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 boom. Let's do a 2D job here. You had 2 comma negative 3, right on. And you added 6 comma negative 5 to that. What would you get? Well, I don't know. Let's find out. 2, 1, 2, negative 3, 1, 2, 3, boom. Should have gone down a little further. There it is. Cool. Nice. Nice. And now if I add 6 to that, so I'm going to go over 1, 2, 3, 4, 5, 6, down 1, 2, 3, 4, 5. Put me right about there. Nice. Hey, where am I located? The resultant vector, just like we've always done, the resultant is going to be 8 comma negative 8. And you're done. You're home free. Okay. Pretty easy to do. I don't think that's going to kill anybody. I don't think anybody's going to be terribly shocked at that. Hopefully that is nice and reviewish for you. Some people have a hard time with vectors. I get that. At first sometimes maybe it's not as obvious. 3 comma 6. If this is the point. Oops! Don't do that, stupid. If this is the point A. Lord have mercy. I'm losing my marbles. And this is the point B. Then the vector A, B, that is you start at A and you go to B, is going to be 10. How do I do that? Because I took 7 minus a minus 3 is 10. Negative 3 minus a minus 2 is negative 5. That guy right there, so I wouldn't write it like this. I would write it like this because it is now a vector. Okay? I will take it written this way too. That's just fine. We don't do it in linear algebra as much as we did in vector calc, but it can be written thusly as well. You could write 10i minus 5j. And we'll talk a little bit more about that. I is the unit vector 1, 0, 0. And j is the unit vector 0, 1, 0. And k is the unit vector 0, 0, 1. All 1 unit long, so all in the x direction, all the y, and all in the z direction. In a 2D world, you would just not include. If you didn't include that, we would know you're talking about just a 2D deal there, and I'm not going to be upset about that. You don't have to worry about the fact that, oh, hey, there's 0 k's as well. You didn't mention it. I'm down with that. Okay. Nice. Now, some things to talk about as well. Obviously, everything you can do with vectors, you can do with regular numbers in terms of all the normal products. Like, ooh, hey, is u plus v equal to v plus u? Of course. Why? Commutative property of addition. Duh. No big deal. Associative property also holds, of course. Why? Because it's just addition, and the commutative property of addition is true regardless. Sorry, I didn't hit shift hard enough. Or I did hit shift, I should say. Yeah, so here we go. U plus V plus W. You can add those two first, or you can add those two first. Whatever. So those are the same. There's an identity. That's not shocking. Hey, when you add the inverse, you get 0. Duh. Things like that. We've already talked about, and we've already talked about scalars a little bit. As far as that goes, that's the big takeaway from section 1 that I want you to remember. The book will use this terminology a little bit. And they will call this a linear combination of some vectors. What do I mean by that? It means you're multiplying by constants and then you're adding or subtracting, potato, potato, vodka. So if you had a u vector that was, I don't know. I'm gonna write this way just for fun, huh? 7, 1, 4. And v is -5, 0, 9. And w is 22, -17, -68. Nice. Then what you'd end up with is 4u would be 28, 4, 16. 6v would be -30. A goose egg in 54. Minus w. What are you doing, you freaking loser? Cool. So 28 minus 30 is negative of those. -2 minus 22 is -24. And 4 minus 17 is 21. And that is 70 minus 68 is 2. Done. Okay. So linear combination. We'll be doing that a lot later on when we get to some other actual applications, which makes it pretty good times. Pretty easy to do. Excuse me. Okay. Standard position is something else that is when they say that the vector is in standard position, they mean starting from the origin, but it's a positive x-axis, positive y-axis, and so forth. Okay, so always going to draw it out like that. Everything that we talk about in this first section, as far as graphing purposes, everything we're going to talk about is 2Ds that you can actually sketch it. So if you had, I don't know, vectors 2, 1, and you wanted to subtract 6, 3 from that. Okay, well 2, 1 is here. We want to subtract 6, 3. Now, subtracting 6, 3 is the same as adding -6 and -3. In other words, it's the same vector, it's going the other direction, which that's not surprising. So from here, I'm going to go 1, 2, 3, 4, 5, 6, and down 1, 2, 3. 1, 2, 3. Yeah, good. And so I'm going to come back to here, and voila, there's my final product. Now, where is that resultant vector? Well, as you well know, it's -4, comma -2. Okay. Nice. I don't think anybody's terribly shocked by that. Again, the magnitude of this vector would be the square root of 16 plus 4, which is the square root of 20. The magnitude of this guy would be the square root of 5. It's 36 and 9 is the square root of 45. Or if you're weird, 3 root 5. Yay. Okay, you will not get extra credit from me for that. I don't care. If you do, it's fine. Makes no difference. Just be aware of that. Kind of fun, kind of interesting to do. I think kind of a good time. Yeah. Yep. Ooh, here's a fun one. Here's our XY axis. I'm going to draw a hexagon. And the hexagon will be centered here. And it will have yep, and figure 124, there it is, yep. Center the origin, express, yes, good. So, they have it drawn out kind of like this, where that's A, here's B, here's C, here's D, E, and F. Cool. Nice. So it says this. And express each of the following vectors in terms of OA and OB, where this is O in here. Okay? And so A is equal to from O to A. And B is equal to O to B. Nice. So AB. How would I get this vector? They would go from here to here. How would I get that? We'll start with a nice easy one. When our vectors in question are OA is this fella. And I hate this. I can't make this. And OB is this fella. Okay? Well, when you do that, what do you end up with here? Or how's that going to work for us? Okay? So clearly it made a triangle. It's not quite the right triangle that I wanted. I feel like something's a little weird about that. It seems odd to me. So how would you pull that off, people? So what if you came out here and you drew this guy out like so, yes? Which is who? That guy right there is B. And I need to get from here back over to here. So I'm going to do... Oh, come on. Where's my yellow one? I'm going to do B, and then I'm going to do minus A. So AB is equal to B minus A vectors. Okay? Let's do another, shall we? Cool. Oh, nope. Shoot. Go back. Cool. What if I wanted to do... Not that one anymore. Sorry. What if I wanted to do vector AD? AD. Well, how am I going to get from A to D? From A to D? Well, I feel like what I need to do is I need to take A, this guy right here, and I need to flip him around. And so I need to flip him around, and to do that, I would end up with what? I would end up with negative A. Yay. Now, that would be from here to here, yes? So that would get me from there to there, but it wouldn't get me from A all the way over to there, yes? So to do that, I'd have to get from, to be at A, I'd have to be at where? I'd have to have A already. I'd have to go minus 2A to get back over there. I'm sorry, from A to D. I'm sorry, from A to D is just minus 2A. Yep, there you go. It's minus 2A. I forgot where I was going. I'm going from A. I'm not going from the origin. I'm going from A. So I need to go A. I need to go to negative 2A from there. There you go. Back to D. Let's see here. What if I did CF? CF. C to F. Good night, nurse. That's this direction. How are we going to do that? How? How indeed, friend. How indeed. Well, what do you think? Clearly, this fella here is going to be involved. Clearly. Okay. Seems like if I went from here to here, remember this is a hexagon, so what do we know about these two guys here? They're the same length, right? It's a regular hexagon. So from here to here is A. If I go out another one, that puts me another A, I think, yes? That's 2A. And then if I came back, the negative B, and another negative B, it puts me there. So it's going to be something like 2A minus 2B, I think. Oh, it's not I think. It is true. I was just a little confused. Pardon me one moment. Okay, now let's do one more for fun. So BC plus DE plus FA is equal to what? I don't know. So I need to go from BC, so that's a negative A, and then I need to go from D to E. So I'm taking DE like so, DE, okay, plus FA. If I take DE and then FA and add them back together, what do I get? I just get another a, yes? And so I have a negative a plus an a, 0. 0 is where we'll end up. Notice it's not 0, it's the 0 vector. I have the zeros in both of my x and y components. I didn't go anywhere in that case. Okay? So that's all pretty dandy. It's pretty nice. It's not too difficult. I don't think you'll find. And again, this should be reviewed for most of you. Not a horrible thing at all. Later on, we will be getting into, of course, the idea of the dot product and whatnot. So if you're hang tight for that, we're not there yet. Okay. In this book, they'll make a big deal about being whether we're in R2 or whether we're in R3. That just means three dimensions or 3 dimensions or 2 dimensions. And I'm sorry, I wrote them in the wrong spot. R2 or R3. That's why your book writes it. Okay. Not to be confused with this or this. Oops, what are you doing? That's a Z. Okay. Where are we talking about binary or base 4, base 6, or base 11, or whatever the heck it happens to be in. Okay. So on those problems, I'll do a few of these. I'll assign a couple of them just for grins, I guess. I think they're kind of fun, but don't get too hung up on it at all. I don't think they belong in here. I think it's kind of fun to do just for fun, see if you're paying attention, but it's not that big a deal. For instance, if you had 2 times 2 times 2 in base 3, what would you get? Well, that's 8. And what is 8? And we call this, we could talk about being in mod 3. What is 8 mod 3? In other words, what's the remainder when you divide by 3? 3 goes into 8, 6 goes in once, or twice rather, which is 6, remainder of 2. That's your answer, 2. Okay. Or if you had 5 times 6 times 3 is equal to, all right, well, let's put it this way, is equal to, well, you can write this way too if you want, is equal to blah and mod 5, for instance, is one way to do it. It's the mod 5 stuff. So if this were true, you could write this way, or you could also say it's equal to blah mod 5. Now, if you think about that, that's 30, that's 90. Hey, what is 5 goes into 90? How many times? I don't know, but it goes in with no remainder, so 0 is what you're left with. Had this been plus 1, then it would have been 91. 91 divided by 5 goes in however many times with a remainder of, in that case, it'd be a remainder of 1. Okay. Very, very straightforward deal there. It's kind of fun. There's some fun things to look at in terms of patterns, too, if you want to. So like this one here, 2 to the 17th power in, well, let's do it this way. Let's do this first. 2 to the 100th power is equal to blah mod 11. Okay. And how in the devil are you supposed to figure that out, Jay? I asked a good question. I don't know. So what I like to do is I go 2 to the 0, of course, is 1. 2 to the 1 is 2. 2 to the 4 is, 2 to the 2 is 4, rather. 2 to the 2 is 4. 2 to the 3rd is 8. 2 to the 4 is 16. 2 to the 5 is 32. 2 to the 6 is 64. 128. Jay, isn't there an easier way? Couldn't you just use a spreadsheet? Of course you could. I'm not there yet. Bear with me, friends. And so what is this? If you divide by 11, you get, goes in 0 with remainder of 1, remainder of 2, remainder of 4, remainder of 8. 11 goes into this once, remainder of 5. 11 goes into here, 22, remainder of 10. Goes into here, 5 with the remainder of 9er. Goes into here, 10, 11, 11 times the remainder of 7. Good night, nurse. I can't do math in my head anymore. Let's jump to Excel, shall we? I feel like it. Cool thing about Excel, if you don't know this, it does modular arithmetic pretty nicely, but I'm going to do it this way just for fun. So equals 2 to the 0 equals 2 to the 1th. Oh, actually, I should just do this. Equals 2 times 2 times the previous feller. Whee. Okay, cool. And of course, in Excel, you could drag it down. Then you go equals mod this guy, comma, 11, which is what we were doing. Nice. Hey, wait. Oh my gosh, the pattern repeats itself again. What? Now, who saw that coming? Well, it repeats itself every how many? Well, you're like, well, it repeats itself every 11. Yeah, well, every 10 more. Yes? So 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4. 0. This is 2 to the 7, 2 to the 8, 2 to the 9, 2 to the 10. Okay? 2 to the 20 should be repeated again. Oh, darn you, you hippie. 2 to the 20, that's the 20th power, correct? So 2 to the 100th power, being a multiple of that, should end in a 1. Okay? And that's kind of a slick deal. You're like, well, can I just drag it in Excel? Actually, you know, the computer will tell you to take a flying leap here pretty quick. Screw you, I'm not doing it. Well, it'll give you times 10 to the blah, 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 blah power, but it's going to round off the last 87 digits. So good luck with that. Yep, see, good luck. And so that is where some patterns, of course, come into play. And, of course, I'm sure most of you know that already. It's not a huge, huge deal, I don't think. Now, that pretty much takes care of what I want to talk about from section 1, just a little review of vectors. They're kind of fun there. It's kind of a good time. Section 2, we're going to be doing the dot product. Pardon me while I get my pen switched back around. I don't care for brown things. That's weird. It's not the 1970s, boy. There we go. Nice. The dot product. So if you've never seen it before, U dot V. Well, it's weird if you've never seen it yet, but that's cool. How do we do it? Well, so let's write this out here. So if U is equal to U1, or UX maybe, comma UY, UZ, whatever, and V is equal to, I don't know, Vx, Vy, Vz, then this dot this is going to be equal to Ux times Vx plus Uy times Vy plus Uz times Vz. And that's it. You're done. So, for instance, if this was your U and your V was equal to -6, 0, -4, and U dot V would be equal to -18 plus a goose egg minus 12, which is -30. Okay? And that's pretty slick. It's pretty good times. I personally like where this thing comes from. It turns out that the cosine of the angle between two vectors, when they are butt to butt like so, the cosine of this angle is equal to U dot V over the magnitude of U times the magnitude of V. Okay? That to me is the easiest way to remember this problem in terms of how excited or where this comes from. What do you use it for? To me, that's the kicker. It's a lot of fun to do this problem. We'll work through it in a little bit here, but this is where you use the thing. All right. A thing I don't like about when you look at a linear algebra book is like, oh, this is exciting. Let's talk about the cool things that you can do with the dot product. Did you know that it's associative and commutative and so forth? Yeah, I did. I did, yeah. For instance, U dot V better be equal to V dot U. Why? Because it is addition and multiplication, both of which are commutative. So you would think that the dot product also would be commutative. Hey, you can look at the distributive property here. Does this shock me? Nope, it sure doesn't. Why? Because I can add first and then multiply, or I could multiply, which is distribution right there, yes? I could do that first, if that makes me happy, and then add, okay? Not surprising at all. Could you take and multiply one of them by a scalar first and then dot product? Of course. So yeah, I mean, it's easy money, okay? This one here is kind of fun. What would U dot U be equal to? Let's think about that for a minute. if you had 3, 4, 5 for your u vector, what would u dot u give you? Well, let's take it. U dot u would be 9 plus 16 plus 25. Wait a minute. That's 50. But wait, isn't this a squared b squared? Shut up. This is equal to the magnitude of u squared. Nice. Meaning, if you want the magnitude of u, you simply square root the dot product of u with itself. Okay? That's a big deal, and that is something that you will use from time to time going forward. That's kind of a big deal. It's pretty easy to do. It makes a lot of sense if you stop and think about it for a minute. What would happen? Let's go back to this thing here. If you took this cosine of theta, u dot v. Of course, if neither one of them, u not equal to the 0 vector, v not equal to the 0 vector. Okay. Obviously, I say that because obviously they cannot have magnitudes of 0, because if you did, you have 0 in the denominator, plus it'd be kind of screwy. They wouldn't be a vector technically anyways, but whatever. What if this thing here, what if u dot v equaled 0? What if that happened? What if? Well, then you'd end up with the cosine of something is equal to 0 over not 0, which of course is the same thing as saying 0. And so what is the inverse cosine of 0? Inverse cosine of 0 is 90 degrees. So if u dot v is equal to 0, then u is orthogonal to v. Now, if you've not heard that before, I apologize. I keep thinking everyone's pretty much going to be coming from vector calculus. So if you've been there, you know that's a big deal. Orthogonal just means perpendicular in more than just in 2 dimensions. Okay, so once we're 3 dimensions, we say orthogonal. Beyond that, we just say orthogonal anymore. We don't really get hung up on that. But that's in essence what it means. Okay, so think about that. That's a big deal going forward. We will spend a lot of time on that. Later on, we start talking about basis matrices. And you don't even know this right now, but basis matrices. And we start talking about a base matrix, and we start talking about independent vectors. If they're truly independent, then they will A, create a basis matrix, and then B, they will be orthogonal to one another. Okay. The good news with that being is obviously if you're running a statistics kind of a test, you're going to do something there, you'd like to have 2 vectors that are independent of one another. If those are your 2 explanatory variables, we call them, or if you will, your x's, like how long you stay in the sun and how much suntan lotion. Both of those are independent of one another. I mean, when I was a kid, we played outside all day long, never wore suntan lotion. We call it, once in a while, Mom would smear some suntan lotion on you. And in the 80s, the gals on TV and the newspaper, well, not newspapers, magazines and whatnot, they were always like, looked like they'd been in the oven for 3 or 4 hours. And they're just nicely crisp. But they had their nice suntan lotion on, like an SPF of like 4 or something. And once in a while, Mom would smear some of that on us. But most of the time, we'd go outside, turn beet red, come back inside, peel, be pasty white again, go back outside, do it again. And so one of these years, it wouldn't shock me if, I come down with some melanoma or something, because, well, that's just how it goes. It made no difference to me at all how long I stayed outside, whether I had suntan lotion on or not. Just was outside, all the time. And nowadays, I think it's probably the same kind of a deal. Everybody gets a SPF 97 before they step out the door nowadays, it seems like, in the summertime. And it doesn't really matter whether it's on or not, because those kids are not going to stay outside for very long, it seems like, anymore. But that's just, that's what I've noticed as I get older, I guess. They're independent. However, both of those would impact how likely you are to get sunburned, and the amount of time you stand in the sun, and whether you're wearing SPF, 14 or not. Okay? It's kind of a big deal, and kind of fun there in that regard. Okay? Nice. let's just do one here for fun. Suppose you had, I'm going to do a vector that looks like this. And a vector that looks like this. And I'd like to find theta, which is the angle between them. That's what I'd like to know. Can we find that? Sure, let's do it. So, u dot b, or a dot b, would be -3. 2 plus 2 is 4. 1 times 9 is 9. So that's going to be 13 minus 3 is 10. Now, the length here would be 9, 13, square root of 14. And this is 81, 82, 86, I think. Let's grab a calculator here. Cool, all right. Now be careful. When I'm doing these angles like this, I prefer it to be in degrees, but you do you. Just be aware that when you go check your answer in the back of the book, it may have decided, for whatever reason, no, we're going to use radians this time. Okay, cool. Another time, mostly it's going to be degrees. 10 divided by the square root of, and remember, you can put them both inside the parentheses, or both inside, I'm sorry, the radical there. And you will find it's that answer right there. And when you take the inverse cosine of that, inverse cosine of that, you will get about 73 degrees. Right? Yay! Cool. Come on, Betsy, give me a new page. There's a couple of inequalities that they bring up in this section. One that you've known since you were like in, I don't know, well, whenever you took geometry. I took it in sophomore year of high school because I was an idiot and I lived in the sticks and that's all we had. And I hate it. But whatever. Not that I live in the sticks. That's the best part of it. The fact that I'm an idiot and I hate geometry. I mean, the triangle inequality. I also hated that. I taught it twice. The next time someone tells me I have to teach. Next time someone tells me I need to teach geometry, I'm going to quit teaching. Hate it. Okay, but this one's pretty straightforward. Think about this. The easiest way to draw the picture is to draw them just a right triangle wise. Boom. 4 plus 4 is 8. If you will. But then this side here, of course, is the square root of 4 plus square root of 16 plus 16, square root of 32. Square root of 32 is, well, it's less than 8. And that's always going to be a true statement. Always, 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 always. The only time they'd be equal is if the vectors were in the same direction. Okay? Take these vectors in the same direction, of course, they're equal the same. Yay, then they're equal. That's called the triangle inequality. Okay? When I was a kid, well, actually I shouldn't say that. When I was teaching, but I was young, so I don't know, I'm not too old as a teacher. It used to just really piss me off. I'd throw a random weird triangle on the board. All right, so it's like 7 and like 9 and like, I don't know, 15. Some kid would be like, "That's a groom, that's not a real triangle." And I'm like, I know! Leave me alone. Okay? So, I'm sorry, no, like, I'm sorry, 7, 15, and then like 19 or something like that. And they're like, "No way, that can't be done." I'm like, "Sure, oh. Yeah, you're right. It can't be done." Yes. So that wouldn't work, again, because if you took these two guys here and you straighten them out, they'd only come out to about there. Okay, they have to be longer than the third side. That's triangle inequality. The Cauchy-Schwarz inequality is this one here. U dot V is less than or equal to the magnitude of u times the magnitude of v. Okay. So think about that one for a minute. Think about that one and see what happens here. So I think quite clearly if you had this guy and they're like this, we know that u dot v is equal to what? Well, it's equal to 0, right? And what would happen if they were complete opposites of one? If they were going 180 from each other? What would you get here? Well, if this guy would be like 2, 0, This is going to be like negative 2 comma 0. You're going to get negative 2 times 2 is negative 4, and then plus 0 is negative 4. Then if you take the absolute value of that, of course, you get positive 4, right? So positive 4. Now, because they're 180 opposite of one another, you're like, oh, well, what's the magnitude of this guy? Well, the magnitude here is 2. The magnitude of this guy here is, well, 2. 2 plus 2 is 4. 2 times 2, I'm sorry, is 4. Hey, look, it's equal in that case. And it's also true if they're going the same direction. If you had 2 going the same direction, it'd be like, for instance, it was just 2 and 2. You get 2 times 2 is 4, plus 0 is 4. And then you'd get, what would you get again? Well, you get the magnitude of 4, the absolute value of 4 is 4. And then, of course, these have the same magnitude as well. That's a pretty easy one to visualize. Anywhere between here and here, what are you going to have? Well, you're going to have not all of it. And so the way I like to think of that is this, is I've already shown you this picture. Okay? And we know that's the cosine. And so if I write this u dot v, or I mean, I'm sorry, these guys here are not dots. These are the magnitudes of each other, times the cosine of theta. Okay. Now, if you just pardon my just pretending for a second, suppose I just ask you this. Cosine is always between negative 1 and positive 1, yes? But let's suppose I took the absolute value of that, yes? Then I'm looking for a number between 0 and 1, correct? I'm looking for a number that's between 0 and 1. If I take the absolute value, I have to take the absolute value over here as well. Now think of what that does for us. You're saying that these guys here, you're going to be multiplying them times a what? Well, you're going to be multiplying them times a decimal, correct? Right? So if you think about that, let me rewrite this problem around so it's the way that the Schwartz inequality is given. The way that the Schwartz inequality is written this way. Well, I'm sorry, in this order, I should say. So who is the bigger number? Well, this number here, again, is less than, or well, between 0 and 1, right? So when I think about that, that means these numbers here have to be bigger than these numbers here, correct? And so in general, these guys here are bigger than or equal to this guy right here. Equal to when they're either 100% opposite or 100% in the same direction. If there's anywhere in between, obviously that they're going to be some fraction thereof, and these guys have to be bigger than those guys. Yeah. Now that picture, when you put it together, obviously comes back up here as well, because obviously these guys here have to be what? The biggest they could ever be is the equal to the top. And why is that? Well, because it's a triangle, right? If you think about it, when I draw this triangle out here, what I'm looking for is this picture, yes? Well, that's a right triangle. Okay. So it has to work out that kind of a way. We're talking about a right triangle that we're building based on these parts, where that's the hypotenuse and that's the adjacent side. Well, the adjacent side can't be any bigger. That's in essence what we're saying. Okay, so that would be the adjacent side, and this would be the hypotenuse in essence to what we're drawing up. So that's just another way. That's the way it's always stuck in my mind. So a lot of people kind of try to draw it a little different. Yeah, whatever. It's the same. And let's see what else do I want to do. I'll do a few examples here and we'll get going there. We already talked about that. Good old Uncle Pythagoras. Vector u plus vector v is equal to this guy. Oops. If what? If u and v, well, obviously if it's a right triangle, right? This side squared plus this. So if you think about this, this is not true in any other triangle like this, right? If this is u and this is v, then u squared plus v squared is not equal to that guy. Okay? This is only true if this guy here is 90 degrees, correct? All right, so if u and v if and only if u is orthogonal to v. Okay? Nice. All right, do a couple examples here, and we'll have some fun with it. See where we end up. Oh, 5, 4, -3. Nice. And I'd like to find the angle theta. Let's do it. Oops, a daisy. So the dot product is 5 plus -8 plus -3 over 25 and 16 is 41. That's 50. 1 plus 1 is 2 plus 4 is 6. And so this comes out to be, I think, that's 3,000, stupid. Yes, now let's take the inverse cos. 110 degrees. Hey, does that make sense? It surely does, sir. Why? Because that guy right there is what? Negative. Think about that. Remember, theta, or cosine of theta, rather. Inverse cosine. Try again, Jay. Inverse cosine is defined between where and where? Between 0 and 180, correct? And so clearly if the cosine's negative, we're going to be in the second quadrant. So think about that. The biggest you'd ever get is 180. That means they're completely opposite one another, opposite directions. Obviously, if 0, again, you didn't go anywhere. You went straight up, so 90 degrees to one another. Nice. Ooh, here's a fun one. Rectangle, ABCD. Oh, I don't want to do that one. Oh. Sure. I'll do it anyway. I don't care. A, B, C, D, 1, 2, 3. That's where point A is. And point B is at 3, 6, -2. And C is at 0, 5, -4. And then D is equal. Uh-oh, we don't know where D is. Uh-oh. Determine the coordinates of D. Now, interesting. Nice. Okay, so what do we know? Well, we know that A, B, C, D. We know that A, B, C, and D, well, we know we have to have opposite sides. They got to be parallel and congruent, right? So let's do this guy here. We go from A to B, we're going to go, it's 2, 4, -5, I guess. Is that right? That's the vector from there to there. And from B to C, we're going to go from, we're going to go -3, -1, -2. And then C to D, oh, we don't know C to D, do we? Nice. Now, as you're doing those, what do you notice? Okay. Well, first of all, you should notice that this dot this should be 0. Let's see if that's true. It's -6, -4 is -10, plus 10 is 0. Hot dang! We're right there. What you should also notice is this top guy is the squirt of, that's 4 plus 16 plus 25, square root of 45 units long. That's cool. And this guy here should be the square root of, it's 9, 10, 14. Square root of 14 units long there, I guess. Nice. Nice. Nice, 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 nice. Oh, here's a question for you. How far is it from here to here? Let's find out. We went from there to there. It's -1. And it's 3 and -7. Right? Isn't that true? I think so. I think I'm right. Nice. All right, so what did I want to do with that? Well, I need to make sure that I have the same distance going this direction, yes. Okay. Just a second. Sorry, I'm back. Now think about this. This bottom vector has to be the same as the top vector because they're parallel, okay? So that bottom vector has to be that way. Well, we know we're at C here, correct? Okay, so we had to start over here somewhere and go to C. And to do that, we had to go over 2, over 4, and then down 5, if you will, right? So I'm at D, wherever D is, and I'm going to go, I've got to go 2 in the direction, I got to go 2 in the X direction to get to 0. Well, that puts me at -2 to start with. And I had to go over 4 units, you see, to get to C. Well, C is at 5, so I had to start at 1. And I had to go -5 to get to -4, which means I started at 1. Okay. Now, is that also true going from here to here? Well, I think so. Check it out. This side here is -3, -1, -2. Well, if I start at A, and I go -3, it puts me here. If I go -1, it puts me here. If I go -2, it puts me there. Sure enough, there it is. And then the question is this length here the same as this length here? Now, vector-wise, it was this distance here. It was 1, -3, -7. Is that also true? Well, look at B here. Well, if you went from, so you're like, well, is it going to be the same vector? A lot of people would think it's going to be the same vector or the negative. No, the vector is completely different, but the length must be the same. So D is the point. I'm going to write this out of my way. It's kind of annoying me. D is the point -2. Oh, vector's stupid. It's a point. -2. What did I say? -2, 1, and 1, I think. Is that what I said? I think so. So then if you look at that, from B to D is, or D to B, whichever way makes you happier. From here to here is 5. From here to here is 5. From here to here is -3. Oops. How long is this vector? That's 25, and 25 is 50, plus 3 is 59, or plus 9 is 59. And then this is 49, plus 9 is 58, plus 1 is 59. So in other words, what I tried to show was that the diagonals must be congruent, and they clearly are. Okay? And therefore, because my rectangles are congruent, my opposite sides are the same length, but they also, because of the same vector, they have the same angle, clearly. Okay? That's how you know. And if you show this one is 90 degrees with this one, then this one has to be as well, because this guy is parallel to that guy. Okay? And that's all you needed to show. In Calc 4, if you have my class, we did this in class quite a bit. I want to just demonstrate this to everybody, and that is the idea of what's called a projection. And we have a scalar projection, and a vector projection. And I personally find that it's easier to teach vector projection, and we'll get to the scalar part of it later, but whatever. So, me personally, doesn't really make any difference how you draw this picture. There's an angle there somewhere. I'm going to do B onto A. The way I like to draw the picture, I draw the sun up here. It's directly in high noon. It's the Raisin Brand sun with the Ray-Bans on. Cool. The shadow is straight down, of course, forming a right triangle. Okay? This whole bottom vector is vector A, and you're projecting the shadow of B, you see, onto A. So this length from here to here, this is the scalar projection of B onto A. And the way that your book writes that, actually your book does not break it out, which makes me even happier. I forgot. Your book does. My other book does. This one doesn't. That's good. And then the actual vector from here to here, the actual vector, not the length of the vector, but the actual vector itself. The vector itself is the vector projection of B Okay, nice. Now, what I would like to do is this, honestly. If I'm looking at this guy here, this looks just like a cosine problem, doesn't it to me? If I knew the hypotenuse and I knew the angle, it's just the cosine, am I right? So this is just really the absolute value, or not the absolute, the magnitude of b times the cosine of theta. Oops. Times the cosine of theta is, what if you think about that? Well, what is that? Well, it is the scalar projection. It is the length. Okay. But wait, what is the cosine of theta? That's a good question. Well, last section, or earlier this section, we talked about that was the a dot b over the magnitude of a times the magnitude of b, right? Wait, but that simplifies to just this, a dot b over a. That make sense? Nice. Nice. This is just a length or a scalar. If that makes you happy. By the way, sometimes the dot product is known as the scalar product because that's what you get out of it. You get a scalar when you're done. Okay? Nice. Well, that's hot. Well, which direction is this going? Well, it's going in the direction of vector A. Wait. If only I could find a vector that's going the same direction as A, but has a length of 1. Dude, you can. Check it out. What do you have here? This is what is referred to as a unit vector. It has a magnitude of 1. So if I were to take this guy here and then multiply it by this scalar, what I would end up with is I would end up with the vector projection, where this is the magnitude and this is the direction. Together they form a vector. Okay? Remember, scalar, scalar, scalar. That guy right there is still a vector. So it's all scalars. Now, a book that I teach out of in Calc 4 writes it this way, and it actually makes it a lot nicer for the calculations. But it's the same. Your book writes it this way. Which is the same thing. And they write it, of course, as the projection. Oops, they don't write the whole thing. They write the projection of B onto A. Okay. So however you like to write it, makes no difference to me. This is probably the easiest math-wise. This, I think, understanding-wise, is the easiest piece of it. This piece here is just the length of that bottom part of this triangle right here. And then simply this piece here is just a unit vector in the direction of A. Boom, you're done. Okay. I think I'll do an example of this, and then we'll look it up on a graph real quick. And then there's one more thing I wanted to cover today. Wait, where's my... You go away. You go away. Go away. Yeah. So let's do this. 3, 1, -2. Let's make this our A. This is our B. 6, -2, 1. So let's do the projection of, let's do A onto B. That's weird, Jay. It's just backwards. Yeah, I know. It's no big deal. So when you do it, again, the formula will be the same, except that you're going to have B okay. Whoever you're projecting onto is the one that shows up all the time. That makes sense? And you'll only have one of the other ones. Okay. So let's see what happens here. So again, I think it's easier if you write it this way. I just think it's easier, but you do you. Or if you prefer, you can rewrite this as B dot B, which is really what you're doing when you're finding the magnitude squared, right? Okay, so here we go. So A dot B is going to be 18 minus 2 over 36, 40, 41 times 6, negative 2, 1. So 14 41st, whatever that is. And I'm going to go ahead and do this on the calculator because I want to graph this in a minute just so I can visualize it more better-ish. 14 divided by 41. And I'm just going to put these in as a vector because I can. There they are. Cool. Nice. All right, so I'm going to go to. Come on, give it to me. Come on, where's my keyboard? Oh, yes. Calc. Plot. 3D. Cool. Calc plot 3D. Yes, I meant cake plot 3D. Of course I meant that, you idiot. Anyway, I use this a ton in my vector calculus class. If you have that from me, you know that. If you don't, that's cool. I do. Here it is. You go away. Let's add a vector, shall we? And our vector is going to be a different color because I like mine to stand out. No, don't. No. I'm uploading. You can't do that. You can't do that. You hippie. Oh, you better still be uploading or I'm going to be not pleased. Oh, I'm going to be displeased. Great. Oh, you hippie. You. Oh! Mother of pearl. I'm going to smack you. Okay, I'm going to be just beyond upset if my upload is not done. Go ahead. Tell me you had a problem again. No. Was it still uploading? Oh. Cancel upload. No, I don't want to cancel my upload. Keep uploading. Ooh. Are you still uploading or not? I can't decide if it is or it isn't. I guess we'll let her sit for a few minutes. Cool. Anyway, whatever. Calc plot 3D. Let's try that again. Okay. Goodness sakes. Brother. I guess I better use my keyboard. Alright, so my vector was 84 41st, comma, negative 28 41st, comma, 14 41st. Cool. And let's make him stand out. Nice. Cool. There it is. There's my vector heading out that way. Okay. It's ridiculous, Jay. Why did you make it? Okay, there it is. I can see it now. Okay, now I'm going to add two more vectors. The vectors I'm going to add are the original vector, which was the original two vectors, which were, oops. 3, 1, negative 2. 3, 1, negative 2. And 6, negative 2, 1. something went boobered. 6, -2, 1. 3, 1, -2. Did I type that in wrong? Stop it. Stop it. Stop it right now. Well, I made a little boo-boo somewhere. Pardon me while I find my boo-boo, and I'll get right back to you. No, I found it. I'm an idiot. I didn't put a slash there. I put a comma. I'm not even sure how it graphed it, to be quite honest with you. Hey, look at that. It's going in the same direction. Oh, what? Something's a little screwy there, Jay. It's a little less screwy. Still isn't correct, though. Okay, I just retyped that one in, and it's sitting right on top of that vector. You see that? That's what's supposed to happen. I don't know what my problem is. Just not the computer hates me, probably. Oh, Jay, don't be a drama queen. Well, this is what was supposed to happen. This guy here, this last one that I made, the pink one or purple, whatever, was reflected down onto the shadow is the red. The shadow is the red one, and it's laying on the black one. That's what's supposed to happen. Apologize that it took so long. Apparently, I'm not too swift at this stuff. You'd think I could do it more after all these years, but who knows? All right. And the last thing I'm going to show is, I think, kind of fun. It's a cool thing that I like to do, and when I introduce the dot product, if you've seen it before, you're welcome to tune out. But I'm going to take a couple of cities in the world, and I'm going to look up their airport codes. If we were in class together, I would have you do this together, so this is kind of fun, but I'm going to go ahead and just grab these here. So I did Montreal, and its latitude is 45.5 north, and its longitude is 73.57 west. Okay, now remember the Greenwich mean, the prime meridian goes through Greenwich, England. West this way, east this way. Makes no difference how you refer to it, which one's positive, which one's negative. I'm just going to treat them as one's positive, one's negative. Since I already wrote this, west is positive, I'm just going to go with it. And then I'm going to type in, I don't know, Sydney, Australia, I guess, for lack of a nicer place to go to. Sydney, Australia. Australia latitude. There we go. And Sydney is 33.87 degrees south, 151.2 degrees east. Okay. Nice, whatever. So there's that. So when we do these, and keep this in mind, what we can do is we can actually go in and we can find vectors for these guys. I'm committed now. I'm going to do it. These are basically in polar form. Basically, not polar form, I'm sorry, spherical coordinates. If it's been a while since you've done spherical coordinates, you need a rho, you need a theta, and you need a phi. Remember, phi starts at the North Pole and comes down 0, 180 is down here like so, and it only goes from 0 to 180. This is your phi. So it's going to be 90 minus the latitude. Okay, so for Montreal, it's going to be like 44.5, right? Whatever I have to get to 90. For this one here, it's going to be 90, and this would be like negative, if you will, because in the southern hemisphere, it's going to be 90 minus a minus 33 or 123. And then for theta, we're just going to treat this as positive. We're going to treat this guy here as negative. So this is for Sydney. So for Montreal, what we can do is we can actually, in Montreal, we can actually take this and get an x, a y, and a z coordinate. That is, put them in rectangular coordinate format, which is what I want to do. If it's been a while for you, it goes like this. Oops. And that's what it's going to be. So in this case here, what is rho? Rho is the diameter of the Earth, the radius of the Earth rather, and it's roughly 4,000 miles, give or take. I'm going to go cosine of 73.57, sine of 44.5 degrees. And then this one is 4,000 sine. And 4,000 cosine 44.5. And I'm going to do this on a calculator here. I'm doing it for a reason. It's a very good use for what we're going to get out of this. It's going to be a very good use for the dot product. Something that I know when I first learned that this thing that I'm doing existed, I was like, that's cool. How did they find it? Well, people are all real hazy as far as giving me answers. I'm like, thanks a lot, pal. So 794-ish. Doesn't have to be real accurate for what I'm doing. I'm not like trying to, well, if I was actually doing what I'm doing math-wise, I'd want to be a heck of a lot closer. 2692, let's say. But just showing you how to do it, I don't really care. And cosine 2850. Cool. That's for Montreal. And for Sydney, 4,000 cosine negative 151.2 sine 123.87. 4,000 sine. Negative 2912. Negative 1601. And negative 22. 25. Is that right? Nice. Cool. So these, you see, would be vectors from the center of the Earth. You would come here, here, and here. And from the center of the Earth, you'd go here, here, and here, X, Y, and Z. Is that clear for everyone? Nice. So here's my question. Somewhere, here's Montreal, here's Sydney. What is the angle between those two cities? That's a great question. Well, I would take the dot product, yes, divide by the magnitude of those two guys. Wait, what is the magnitude of this? Well, from here to the center of the Earth is 4,000, that's right. And 4,000, sweet. So all I have to do is the dot product. So, let me show you this real quick. I probably wouldn't do it, but I'm just going to do it here because I can. So 794, comma, 2692, comma, 2850, and close your bracket there. STO, that's the STO button. I like to store it as A. Don't ever store X, Y, Z, or T. Don't ever do that. Word of warning. Don't do it. You'll regret it. I promise. Because then you'll be graphing something and then like, why isn't the dang thing wrong? Because you stored something as X, you goober. That's why. Ask me how I know. Oops. Negative 1601, loser. And then I store this one as A. Stop it. Stow alpha B. I'm sorry. That's what I meant. Now, what you can do is you can go second math. That's the 5 key. 4 is matrices. Clear at the bottom, you'll see vector ops. Under vector ops, you can take what's called the dot product of, and then you just go A, comma, B, like so. And you get that god-awful number there. Divided by the square root of, well, now wait a minute, Jay. What is it, the square root of? Divided by the square root of, well, divided by 4,000. Well, it's, okay, each of them has a length of 4,000. So it's the magnitude of each. So it's 4,000 times 4,000, right? Stop it. And you get that number right there. And then the inverse cosine of that guy is 144 degrees. Like, that's nice, Jay. What do I care? Well, let's convert that to radians just for a good time, shall we? So I'm going to take that guy times pi, divide by 180. I get about 2.515 radians. What does that have to do with anything, Jay? Well, I'm glad you asked, friend. From here to here is an arc, yes? How do you find an arc length? Remember, S is equal to R theta. So in other words, 2.5 times 4,000. I'm saying it's 10,061 miles roughly between those two cities. So let's go have fun with that. Let's go into here, and if you do great circle mapper, great circle mapper. There it is. There we go. And if you were to type in map, and you were to type in Montreal, and then Sydney, I can't spell too good. Oops, draw a map. Montreal, yes, that one. Yes, of course. Yes, that one. And yes, that's the one I want. Oh, didn't I select it? No, I didn't select it. Just one moment, please. Apparently I didn't select it. There we go. Got it. You will too. Oh, I should just do Sydney here. I'll do Sydney Airport code this way. Sydney Airport code. Sid. There you go. There it is. Boom. There's the map. There it is. And yeah, I'm pretty close, friends. I said 10,000 and it's 9,955. There is the Great Circle Route. Okay. You can zoom on that a little bit, I think. Maybe not. I don't know. Oh, yeah, I guess you can. Anyway, you see where you're flying in there at. Now, remember, if that wasn't quite the way it was, it would look like this. You'd be flying along the edge of a circle. That's what you're actually doing. But across the hemisphere the way we did, the equator the way we did, we're off by a little bit. Okay? That's kind of a cool thing, I think. It's kind of a neat way to use the dot product. To be honest with you, I've never actually plotted my own course that way. I could see doing VFR flight rules, visual flight rules. You know, I'm going to fly from here to Walla Walla or something. That'd be pretty easy to do, I think. But yeah, big long distance flying, no thank you. All right, well, I think that's it for section 2.1 and 2.2. I think it should be fairly self-explanatory. Again, as always, if you have questions, send me an email.